We're going to talk about bit manipulation. Twiddling, fiddling, befuddling bits. What the heck is bit manipulation? Well, if we remember back to elementary school when they taught us the binary number system. Oh wait, they didn't do that. Maybe they should have though. So we speak in base 10. Our numbers count 0, 1, 2, 3, 4, and when we get to 9, it rolls over to 10. We get 2 digits. Same as when we're at 99, add one more, it rolls over to 100. We have 3 digits. Computers speak base 2, also known as binary. So computers count 0, 1, and then it rolls over right there. So then the next digit on a computer is 1, 0. And then if we add another one, it becomes 1, 1. Add another one, it becomes 1, 0, 0. So why is that important? Well, that means when we store a number in the computer, it's stored as a series of ones and zeros. So everything is a bit. A bit means either 1 or 0. So that actually means that if we wanted to store, for example, 32 Boolean values, we could store that in one integer. So integers are 32 bits. Each bit is either true or false. So we could actually store 32 separate Boolean values in the space that we could normally store one number. So there are certain times, like for example, the Maze generation project, where to save space and to make an algorithm more efficient, you might cram many different pieces of information into the space of, say, 16 or 32 bits. So to be able to set that information in there and to be able to read it, you have to be able to do bit manipulation. So let's talk about the different bitwise operators. This is drastically unreadable, for which I apologize. The slides are on the dashboard. You should grab them. But these are the 4 operators. And, or, exclusive or, not, left shift, and right shift. There's some other operators, but these are like the 6 most basic important ones. So let's talk about and first. And operates on Boolean values the same way double and works. So in many programming languages, you use 2 and signs to compare if something is logically true or false. You can compare 2 values. In this case, we're just going to compare 2 bits using the and sign. So if we compare 0 and 0, the result is 0. And is only true if both inputs are true. If we compare 1 and 0, it's still 0. 0 and 1 is 0. 1 and 1 is the only output that results in true. So this kind of makes sense intuitively based on how logic works. But why do we have this like single and operator? What does that actually do? Well, it operates on whole rows of bits at the same time. So if we have this binary string and we do an and with this one, the result is this. So it starts column by column and goes through and does a bitwise and on it. So this 1 and 0 is 0. 0 and 0 is 0. 0 and 1 is 0. Here, 1 and 1 is 1. So the output is only set to 1 when both of the same columns in the input are 1. So it just does the and operation on each column one at a time. Okay, cool. Are we clear on that? So what about or? Or is true if any input bit is true. So 0 or 0 is 0, but 1 or 0 is 1, 0 or 1 is 1, 1 or 1 is 1. So that makes sense too. We're pretty used to or at this point. So what does it look like on the same 2 inputs? Well, 1 or 0 is 1, 0 or 0 is 0, 0 or 1 is 1, 1 or 1 is 1, etc. So again, we're going column by column and applying a bitwise or operation. How about exclusive or? Sometimes people call it XOR. Exclusive or is true if and only if one input bit is true. So if we have two zeros, wait. This is a typo on the slides. In fact, it's such an egregious one, I feel like I should fix it right now. So this is the OR operator, that single bar. The exclusive OR operator usually looks like that. Yeah, it'll go up once I... Okay, so the exclusive OR operator is like a caret. So 0 exclusive OR 0 is 0. 1 exclusive OR 0 is 1. 0 exclusive OR 1 is 1. 1 exclusive OR 1 is 0. So this is the only point at which exclusive OR is different than OR. So let's do it again for this. 1 OR exclusive OR 0 is 1. 0 exclusive OR 0 is 0. So exclusive OR only checks to see if the two input bits are different. If they're the same, it's 0. If they're different, it's 1. So are we clear on exclusive OR? Okay, cool. Why would we ever use exclusive OR? What is it good for? A lot of things. As we'll see later, you can parameterize flipping a bit with exclusive OR. Or in general, you can flip bits with exclusive OR. So if you have some value, it might be true or false, but you're not sure, you can always set it to the opposite value with exclusive OR. Okay, how about not? So this is an operator on one's complement numbers. Because this is showing up in your mazes project, we're introducing bit manipulation a little earlier than we normally would. Normally we would talk about how numbers are stored in a computer first. So you can look up one's complement if you want. For this, it's actually not super important. You just need to know that not flips the input bit. So not 0 is 1, and not 1 is 0. So that's pretty clear. If we just do not on this, then we get the opposite bits flipped in the output. Cool? Cool. All right, so now it gets a little bit weird. Let's talk about left shift. So shifts literally take the binary string and they shift the positions of the digits. So left shift will take these and shift them left. So that's pretty clear. And it does it by padding zeros on the right. So what is this operator here? Well, this tells us how many places to shift. And this is encoded in binary. So this is not saying shift it one place. This is saying shift it two places. Because this is the twos column in a binary string. And so this has the value 2. So we're going to take this string and shift it over to the left 2 columns. So if we look at it, we can see that goes 0, 0, 0, 1. So if we shift that over 2, it should just be 0, 1. And if we look, it is. So it's 0, 1, and then 0, 1, 1, 0. So 0, 1, then 0, 1, 1, 0, with 2 extra zeros padded on the right side. The interesting thing about the left shift operator is it's actually the same as multiplying by 2 because of the way binary stuff is stored. So isn't that weird? I'm going to probably make a mistake because I didn't prepare for this, but let's try and figure out what number this is, and then this one, and see if it multiplied by 2 twice. So this is the ones column. It has no 0 in it, so there's no 1, which actually, interestingly, means that this must be an even number, because the only way this could be an odd number is if it had a 1 in it, and it doesn't. So there's 1, 2, 1, 4, 0, 8s, and 1, 16. So 16 plus 4 plus 2 is 22. So then we're going to multiply it. We're actually just going to shift it over 2 columns. But that's the same as multiplying it by 2 twice, if that makes sense. So now let's see what this value is. 0, 1s, 0, 2s, 0, 4s, 1, 8, 1, 16, 0, 32s, 1, 64. So 64 plus 16 plus 8 is 24 plus 64, 68, 84. Does that sound right? 64 plus 24? 88. There we go. So is 88 22 times 2 times 2? Well, the answer is yes. 22 times 2 is 44, times 2 again, 88. So actually, whenever you multiply by 2 on a computer, there's a very good chance it's doing a left shift. There's a problem, though. What happens if, for example, in our input, we have a 1 in... All right, microphone reactivated. So what happens if we have a 1 in this column there, and we shift it outside the length of bits? It'll just throw away the 1, which means that it won't be a true multiply by 2 because we will have lost some digits. We just threw them out. Yeah, Ignat. Yes, so very specifically in processors, when you do a left shift operator, you can set different flags for how you want it to work, and there's a way you can set a flag so that it wraps the numbers around instead of throwing them away.
That's called a rotate.
Yeah, it's called a rotate. Okay, so now let's talk about right shift. It's the same thing, except for we're moving things right, and we're padding the zeros on the left side. So it's the same as a divide by 2 with a round towards negative infinity. So what does that mean? Well, let's look at this. We have the same 22, and we're going to shift it right twice. So the result is this, 0, 0, 0, 0, 0, 1, 0, 1. So if we figure out what the value of this is, it's 1 plus 0 2s plus 1 4, so it's 5. So 22 divided by 2 is 11, divided by 2 is 5.5. Round it towards negative infinity, which in this case means rounding down, it becomes 5. So right shifts can be used to divide by 2. Generally speaking, when you use a shift, you're not going to use it to multiply or divide because you could just write directly in the source code times 2, and you could let the compiler figure it out for you. Generally speaking, you're going to use shifts to make things called bit masks. So we'll see what a bit mask is here when we talk about bit manipulation basics. So what if we have a string of binary digits and we want to set one of those bits to true? So we have a bunch of zeros and one of those we want to set to 1. Well, the code to do it is actually very simple. It looks like this. So x is the input string, and then position is the position that we want to set to true. So which column in the input string should be a 1. So first we create a mask. So here's what this looks like. So for example, if the input string is this, and we want to set the bit at this position, this is position 5, by the way, so 1, 1, 0, 2s, 1, 4, that's 5. So where's position 5? Well, 0, 1, 2, 3, 4, 5. So we're targeting this bit. We want to set that bit to true. Well, first we construct the mask using the left shift operator. So what we do is we take a 1, which has the value, 1 has the value all zeros except for 1 here, and then we shift it over the number of times for the position. So 1 is here, and we shift it over 5 times, 1, 2, 3, 4, 5, and now we've constructed a mask that has the bit set in the position where we want to set the bit in the input value. So now what we can do is we can simply OR the input value and the mask together, and that result will have 0, 0, 1, 0, 0, 1, 1, 0, which is what we're trying to do. We're trying to set this bit to 1. Yes, Ignat? What if we want to set it to 0 instead of 1? That's called clearing a bit. It's actually the next slide. So any questions about this? This is using kind of like 2 new operators to do one thing. Is it clear what's happening? All right, cool. So having introduced this concept, how do you think we could clear a bit? Given the operators I just told you, I'm actually going to give you like 60 seconds right now to write the clear bit method. Here's a hint. You're going to create a mask just like we did here. The mask might look different or it might be the same. How can you create the clear bit method? So like, feel free to pull up Python, sheet of paper, This is valid Python. This will compile and run. Try it out. Do positions go by index? Yes. So for example, this is the bit at index 0. This is index 1, 2, 3, 4, 5, etc. So by the way, I failed to point out, here's x. Here's the mask we created. We have an OR there. So this is the result. It set the bit that we wanted. There's our result. OK. So enough time thinking about it. Ignat said he thought he might have a way that he wanted to share. How would you do it?
I would create a mask with all ones, except for 0 at a position.
OK. Uh-huh.
And then you AND it with X.
OK, so Ignat said he would create a mask like this, except for it would be the opposite. It would be all ones, and then a 0 at the position he wanted to clear. And then he would AND together the mask and the input. And that sounds good to me. How are you going to create the mask with all zeros, or sorry, with all ones except for the 0?
Well, it would be same.
So you're close. So
And then I knot it.
knot it, right. So it'd be the same code to create the mask. So you get this mask, and then you do the NOT operator, which will flip all the bits that are 0 to 1 and flip the 1 to 0. And then you can AND together that mask with the input. So let's see that here. So here, we create the mask, same exact way. And then we use bitwise AND with not the mask. So here's the same thing. Here's X, here's the position, here's the mask. So now we're doing it at index 2. So 0, 1, 2, there's our mask. Not the mask flips all the bits. We have a 0 at the index where we want to clear. And then we take the input, we do bitwise AND with our not mask, and then we clear out the bit that we wanted to clear. Does that make sense? We think we got it? Bit manipulation, so cool. Wow, I'm elite hacker. Yeah, Adrian.
We actually did put in the Python.
This is actual valid Python right here.
A string or
Oh, a number. Yeah. And actually, in Python, you can specify binary numbers. So in Python, to specify this, I would write 0 and then B, and then 0, 0, 0, 0, 0, 1, 1, 0. So if you prefix a string of binary with 0B, Python will interpret it as a number that you specified the binary for. Why 0B? B for binary. Why not just B? It's kind of just like a convention. For example, hexadecimal, you do 0x. Oh, yeah. You could do a variable just with a B, so you could have a variable named B1000. OK. So now let's talk about how to flip a bit. So this means taking whatever bit is at the position and flipping it to the other one. So again, now that you've seen how we do set and clear, I'm going to give you some time to think about how would you flip a bit. So think about it, write down some stuff, open up your Python. While we think about flip a bit, I'm going to set it back to clear bit so you can look at some numbers. Who thinks they figured out how to flip a bit? OK. OK. Another 30 seconds. OK, who wants to share with me, not Ignat, because he did the last one, how to flip a bit? Yeah, Josh. OK, so Josh says we'll construct a same kind of mask, and then we'll do X exclusive OR the mask. Let's see if he's right, and he is. Hey, look at that. How cool is that? So here's an example input. Here's the position. So we want to flip the bit at index 2, so 0, 1, 2. So we construct the mask. Here's our mask. It's got the 1 at the index that we want to flip. And then here is our input and our mask. So if we do 0 exclusive OR 0, the result is 0. 0 exclusive OR 1 is 1. So it continues that way, not making any changes with the zeros until we get to here. So a 1 exclusive OR 1 is 0. So it flipped it to 0. What if this was a 0? Well, a 0 exclusive OR 1 is a 1. So if this was a 0, the output would have been 1. So it would have been flipped. Yes, Ignat? Yes. So when you pass a position, you can pass an integer, and it will work correctly because all integers are actually encoded like this. So this is just looking at position as a binary number, but you can pass in 5, 10, 23, whatever. Okay, yeah, Nick.
And it's going to return an integer as well.
Yes. So the return value will actually just be an integer. So if you want to look at what the binary looks like, there's actually a command in Python called bin. You can pass the integer that it returns inside of the bin, and it will output a string that kind of looks like this. Okay. So now, let's talk about if we can figure out, is a bit set? So now we want to return true if a certain bit at a given position is set to true, and we want to return false otherwise. So for example, if I passed in position 5, we would go look at position 5 in the input. If it's true, if it's a 1, return true. If it's false, if it's a 0, return false. So how do we do this? This one might be a little different than the other ones, so it is a little different. I'll give you some time to think about it. This one will require more lateral thinking. So how do we figure out if a certain bit is set? Okay. How do you figure out is bit set? Who has an answer, Nick?
So you state the original number, right shift it by the positions, and then answer with 1.
Sounds good to me. So Nick said, you take the original number, you right shift it by position, and then you just return shifted number and 1. So why does that work? Well, for example, if the input is this, and we want to see if the bit at index 5 is set, we take this, we shift it right by 5. So by the way, index 5 is 0, 1, 2, 3, 4, 5 right here. So when we shift this to the right by 5, this bit will end up in the rightmost column. So when we shift it, now it looks like this. And then we can just do a bitwise AND this number and this number. It will be 1, which is equivalent to true if this bit is set. And it will be 0, which is equivalent to false if this bit is not set. Whoa. So cool, yeah. Yes, Alan? Probably not. So Alan said, is this the only way to do it? I doubt it. Okay. This is an easy way, though. All right, so now we're going to talk about two much more complicated ones. We're going to parameterize our set bit and our clear bit functions. So we're going to pass in an input number, x. We're going to pass in a position, and then we're going to pass in another parameter that says whether we should set that bit or we should clear that bit. So if you want to tune out for the next 2 slides, feel free, because it's like pretty complicated and not super important in the grand scheme of things. And in fact, I don't think I'm going to even let you have time to think about it, because I'd have to give you like 5 minutes because it's a little complicated. So let's look at what it is. Whoa, what is this here? So state, if state is 1, that means we're setting the bit. If state is 0, that means we're clearing the bit. So we create a mask like usual. That's fine. But then we return x and not mask, or negative state and mask. Blah. Ooh. All right, so this is a little small, but here's a bunch of stuff. Here's x. Here's the position. So position 5, 0, 1, 2, 3, 4, 5. And here's state 1. So we want to take this and set it to 1. So here's our mask that we construct like normal. That's cool. Here's all of the stuff that we're calculating in here. So here's not mask. Here's negative state. So to know that negative 1 is actually all 1s, you have to know 1's complement, which we haven't taught you yet. So don't feel bad. But you should know that actually when a computer stores the value negative 1, it does it with like all 1s. It doesn't really store it how you might think. We'll talk about that later. Yes, Ignat?
Is there like also an extra one as well?
An extra one.
Like a sign?
Oh, so sometimes people you will see things with like a sign bit. But actually, computers don't work with sign bits for integers. The reason that is, so let's say we have a 32-bit number. Well, we could use 31 of those bits for the number value, and then one of those bits could just be negative or not negative. So if it's 1, it's negative. If it's 0, it's positive. You run into some problems with that. One problem is that means that you have the value 0 and you have the value negative 0. But negative 0 doesn't actually exist. So it complicates the arithmetic, and the way computers normally actually store things is called 2's complement. So if you want to learn it now, you can look it up. Otherwise, we'll teach you about it later. So when you take 1 and you make it negative, you actually get a string of all 1s. So here is the computation of this quantity here. X and not mask is equal to this. So that's doing the same as clearing the bit like we did before. Negative state and mask is equal to this. So that's actually, in this case, the same as the mask. And then we OR those two together, and we get the result that bit is set. So this is this example. Let's look at the same thing, but instead we want to clear a bit. So it's the same exact method, just different parameter for state. So here's X. We want to clear the bit at position 2, so this bit right here. State is 0, so that 0 means clear. And here's our mask that we constructed. So not mask looks like that. That's cool. Negative state. So negative 0 in 2's complement is the exact same thing. It's still all zeros because there's no actual real negative 0. X and not mask is this. So here's X, here's not mask. When we AND them together, we end up clearing out this bit. So we can see that's cleared out. Here's negative state and mask. Negative state, mask. Well, negative state is all zeros. So all zeros and anything is always all zeros. So this is all zeros. Then we do this or this. And here we have successfully cleared out the bit in index 2. So again, like I said, if all this went over your head, or if you don't care about it, that's fine. I'm happy you ignored those 2 slides. But now it's time to pay attention again, because we're going to talk about some cool tricks that you can do with bit manipulation. There's many, many really cool things. This is just a couple examples. So the first one is, how can you check if a given number is even? So this one, I'm not going to call on Ignat yet. Take about 30 seconds. It's a very, very simple one. Think about how can you return true if a number is even and false if it's odd.
Any number or binary?
Any binary number. They are the same thing. But, so, sorry, the point of this is, though, we're doing it using bit manipulation operators. For example, if we did it without bit manipulation operators, we could just take the number modulus 2, check if that equals 0 if there's no remainder. But we're not doing that. Or just call an is-even function. But we're creating the is-even function. OK, who wants to tell me what they came up with? Yes, Dan. OK, so we said for any binary number, check the digit in the rightmost spot. If it's 0, it's even. Oh, but then he thought about negative numbers, and maybe it's difficult if you don't know 2's complement. But do you have some operators for me? OK, Dan's trying to think on his feet in the case of negative numbers. Actually, you don't have to. The rightmost bit will be 0 if it's an even negative number.
Okay, since negative 1 still has a 1 at the end, it should be the case for binary.
Right. So specifically, how do we check the rightmost bit to see if it's 0? Oh, so that's interesting. So we can do the same thing where we check the value of the bit, but we just don't do any shifting. We don't create the mask. And actually, that's what we end up doing. So you can take any input, do bitwise AND with the value 1, and then check if the result is 0. So this is 5, or sorry, this is 6. 6 bitwise AND is 0. So that means it's even. So 0 equals equals 0 is true. Ignat. Is it faster to compare or not? Strictly speaking, it probably is faster to not compare. But
No, like,
you,
not operator.
oh, to use the not operator versus, oh, the comparison operator. Oh, so this is a good point. You could use the not operator instead of the comparison operator. So you could do not x and 1, and you'll get the same results. It's actually probably a little bit faster to use the not operator. Okay, so what if we want to check if a number is a power of 2? This one's a little tricky, so let's just look at it. So a number that's a power of 2 should only have one set. So for example, if it was 2, then this would be set. If it was 4, then this would be set. This one's 8. So what you can do is you can take the input number, you can subtract 1, which if it's a power of 2, subtracting 1 will set the one that was set to 0 and all the ones behind it to 1. So that was 8, this is 7. And then you can compare them together. And if the result is 0, if the result is 0, then it's a power of 2. So that's kind of a cool trick. Yeah, Elliot, sorry, what? Oh, can I explain it again? Sure, let me check the camera really quick. Okay, so any number that's a power of 2 will have only one binary digit set. Why is that? Well, it's because it's a binary number system. So if this were to be the number 2, then only this would be set. The number 4, only that would be set. This is the number 8, so only that one is set. So if we subtract 1 from the number, then what actually happens is the number that was set gets set to 0, and then all the ones following are set to 1. So we can kind of implicitly reason that that would be the case because we know that this is 8. If we look at this value, this is 1 plus 2 plus 4, that's 7. And you can also test it out with other numbers. It's actually just a property of how binary subtraction works. So you can then AND them together, and the result should be 0 if it was a power of 2. Okay. So here's an optional exercise. If this is interesting stuff to you, write a function to count the number of bits that are different between two numbers. So this one's like a little complicated and might take you some time. So if I have two input numbers, I want to see how many bits are different between them. As in, if they share the same bit in the same column, then don't count it. But if they're different bits in the same column, then count it. Is this clear to everyone what this means? Okay. So that's it for the lecture. Here's some resources. You can find them in the slides, more information about bit manipulation. And now I shall leave you to this exercise and working on your TwitterBot project, working on mazes, working on resumes and applying. So go forth and prosper.